Hi there. In this video, I'm going to show you how you can actually use the time-based SD curve profiling while you're in position controlling mode. So basically, to keep the video short, I'm not going to talk about all the aspects of setting of the unit. So in my setup, I'm having a brushless AC model connected to a Solo Uno unit through an encoder. But here, the assumptions I'm having is you've already tuned your controller and everything is ready for kind of going into the testing of the SD curve. To learn about that, we have many other videos about the calibration, about the tunings, so you can go and watch them. But here, the focus will be only the profile generation. So once you go to Motion Terminal, this is our latest version of the Motion Terminal. The tuning section here, you can see I'm now in position controlling mode. All of the gains of my controllers are already set and tuned, and I've tested them while the motion profile setup was in a step or ramp response. Basically, the step response is the fact that whenever you give a reference, Solo will follow that immediately. So all these tunings, all these parameters are already set. I actually don't need to change anything. The only thing I'm going to talk about is this part of the motion profiling setup. So now I'm going to actually put my Solo into time-based SD curve as I'm in the position controlling, so it will be time-based SD curve for position controlling. And as you see, as soon as I go to that, I can see some parameters appearing here for me. For instance, I'm having T1, T3 timings, T4, T6, and so on. And these are the timings that I need to set, and I'm gonna get back to them in a minute. But as you go down, you can see a chart that is appearing for you. So here you can see a simulation of the motion based on the parameters that I'm having here. For instance, if I put the timings just a value as 1 for all of them, which is in terms of seconds, you can see that the profile that is generated will be changed. But let's get back to this and see what's actually the meaning of these numbers. So basically, you can see here the profile that is generated for me is having an assumption that I'm going to go from one position to the other position that is 160,000 pulses away. So this is a relative position. And for instance, in this plot, you can see the motion starts from 0 pulse and then it ends up at 160,000. On the other side, you see there are 7 segments into this plot. Segment 1, 2, 3, 4, 5, 6, and 7. And each of these segments actually defining for you how the motion will be. So for instance, if I put all of these velocity, acceleration, and jerk into the profile, you will see that when I change these parameters here, which are in terms of timings, the shape of the profile will change. But why? The main reason is in time-based SD curve, the timings that you see here are the timings of the segments. So the segments that you can see here are timed between 0 to a certain number. For instance, here is between 0 to 1 second, 1 second to 2 seconds, and so on and so forth. And you can actually set them here. For instance, if I increase the T1 and T3 timing, you can see this part of the curve is actually having more timing. So basically, it helps me to have less jerky motion because I have more time to kind of elongate my profile. And then, as you can see here, the time 1 and time 3 are equal. So the segment 1 and segment 3 will be having the same timings, and thus they will be having same behavior in terms of jerk and acceleration. So for instance, I can also reduce it. For instance, if I put half a second for that, you will see it becomes reverse the story. So basically, I make the motion in those 2 segments a bit more radical, a bit more faster, and subsequently, as the time is reducing, you can see that the acceleration will be different. The shape of the acceleration and the shape of the speed will be different. But on the other side of the plot, this segment, you see we have 1 second, so the acceleration and deceleration are a bit smoother. So basically, this is what you can do. You can tune these parameters as you like. For instance, I'm going to start with putting all these segment timings equal to 1, so kind of having a distributed timing, and you can see the sum of all is actually 7 seconds. So it's the sum of all of these segments. We have 7 segments. Every segment is 1 second, and subsequently I'm having 7 seconds of motion to go from point A to point B, or let's say to go from my current position to the target position. Another point here is this is the target position. If I change this target position in time based, the only thing that will change is the value of these let's say computed parameters, but the timings will be strictly the same. So again, my whole motion will be done in 7 seconds, but probably I will be having different jerk, different acceleration, and different max speed. For instance, if I increase the distance, you see the maximum speed actually increases. It goes from 60 RPM to 600 RPM. And if I reduce it, subsequently it will reduce because you have more time for a smaller distance. So these are all the things that you can play with. You can tune perfectly your graph. The good thing about time-based is the time is perfectly fixed among all the motions. So if you move very small, let's say distances like 160 pulses, that is very small distance, again it will be done at 7 seconds based on the parameters that I said. Or if you do 160,000 pulses of motion, it doesn't matter. Again, it will be 7 seconds because the sum of all these segments is 7 seconds. So once I have everything tuned and I like the plot here, I can send all these motion profiles to my solo, and then I can check it. I can go down and I can start the monitoring. So I'm going to have an eye on the position and velocity of the motion of the motor, and then here I can put the desired position, same as above, 160,000, just to see how the motor will behave. And here is the motion of the motor. So you can see the plot is actually having a very nice and a smooth taking off and landing behavior. So if I zoom a bit more on it, you'll see that so the green plot, which is the position profile, is smoothly increasing, smoothly taking off, and then smoothly landing from 0 pulses to 160,000 pulses. Basically, here we are having less than 10 pulses of error at the end, and the velocity profile also at the same time is very smoothly accelerating and decelerating to land on the desired position. For instance, if I let it run and I want to have different behaviors, I want to examine different behaviors. For instance, in this plot, maybe you want to have fast acceleration in the beginning. So you want to have a very, let's say, fast taking off, and then you want to have very smooth landing. So basically, if I have if I put like 0.2 second for the take off segments like T1 and T3, and then I provide a longer time for the landing part of the curve, basically my profile will be like this. So in the beginning, I'm having a bit higher jerk, a bit higher, and subsequently you can see my speed profile is very sharp here in the beginning, and then when I'm landing into the target, I'm landing actually very smoothly. So let's see what happens with this profile. I set it, I go down. This time I'm going to go from 160,000 pulses to 0. So I go reverse. So as you can see, the profile is different. For instance, here we are having a kind of a bit faster takeoff and much smoother landing, and you can see it better in the speed profile. The speed profile initially has a let's say very steep slope increasing, and then slowly landing on the target. You can have it also differently for different scenarios, but this is very flexible because you can tune the motion profile in a way that, for example, once you're landing, you have less back EMF or less, let's say, regeneration through having slower acceleration or deceleration. And this is very handy for position controlling applications. Thank you so much. Please follow us on our YouTube channel.